Wang from Nazarbayev University. Today, I will talk about predictive concrete pumping and how we connect three pieces, yield stress rheology, fluid mechanics, and machine learning. This work is done in collaboration with Huang, Keqi, Liguang, Chenglong, Tang, and Yikang from the China State Construction Engineering Corporation, CSCEC, the 6th Engineering Bureau. The key objective of this research is how can we achieve reliable pumping predictions. Very briefly, on my institution, Nazarbayev University, which is an English-speaking research university located in Astana, the capital of the Republic of Kazakhstan. The university is relatively young. This year, we are celebrating the 15th year anniversary of the university. Concrete pumping is the main method for placing large volumes of concrete in modern construction. The Burj Khalifa example highlights what pumping can achieve: high performance concrete to extreme heights. And also, this reminds us that pumping is a highly engineered operation. In emerging applications like 3D concrete pumping or printing, the tolerance for pressure instability or blockage is even smaller. To model concrete pumping, we start with concrete rheology. This slide shows some classical references that establish the idea that fresh concrete is a non-Newtonian yield stress material, and that rheology is a bridge between mixed design and processing, especially for pumping of concrete. A common starting point is the Bingham model, which has two parameters: the yield stress and the plastic viscosity. And the Bingham model is widely used because it's simple and works well in many practical ranges. But for many modern concretes, especially self-compacting concretes, the stress shear rate relation can be nonlinear, which motivates more general rheological models. This slide highlights that the Bingham model is not the whole story. The Herschel-Buckley model, which adds a power law exponent, it can represent both shear thinning and also shear thickening behavior. And the literature for on self-compacting concrete shows that shear thickening behavior is frequently observed. So if we keep only a linear model, we risk biasing pumping predictions. Beyond the Herschel-Buckley model, another widely used nonlinear model is the modified Bingham model, which includes the nonlinearity by including a quadratic term. In our recent work, we also introduced a four-parameter generalized Bingham model, which unifies both the modified Bingham model and also the Herschel-Buckley model. And this provides a consistent rheological model for pumping analysis. Here are some real pumping scenarios: long pipe networks and challenging placing conditions. And this is why we need the models that are not just mathematical derivations, but it should be engineering predictive and realistic conditions. Now, on modeling, if we treat pumping as a simple pipe flow using only the bulk concrete rheology, then we often overestimate the needed pressure for a given flow rate. Because the wall region is not, the fluid doesn't behave as a bulk concrete. Kaplan and the co-workers in 2005, they developed a classical model where they introduced the key idea of the formation of the lubrication layer. And they consider the lubrication layer by introducing a slip velocity in the pumping prediction. And that approach corresponds to an infinite thin lubrication layer. This is the physics behind the lubrication layer formation. During pumping, shear-induced particle migration leads to a depletion of coarse aggregates near the wall region, and thus fluid in the wall region will have a much lower viscosity or yield stress compared to the bulk concrete. And this figure shows the measured values of the lubrication layer thickness. They are usually on the order of a few millimeters. So pumping is inherently a two-fluid problem. We have a bulk concrete and also a lubrication layer fluid. To go beyond the slip velocity approximation, later work by Huang and Keqi and Kayat, they developed a two-fluid pumping model where they consider both the lubrication layer fluid and also the bulk concrete using the Bingham model, so which is with the linear model. So this is a major step in concrete pumping. It keeps the lubrication layer region explicitly, and this gives a more realistic pressure flow relation. This is where our recent work contributes to the development of concrete pumping. We generalized the two-fluid pumping model to account for the nonlinear rheology in both the lubrication layer fluid and also the bulk concrete are modeled by the Hershey-Buckley model or the modified Bingham model. Those results illustrate how the changing in the non-linear parameters in bulk concrete and also the lubrication layer fluid affects the pumping pressure flow rate relation. And this shows that the rheological nonlinearity is not just a minor detail. Actually, it affects the pumping prediction quite dramatically. I would like to acknowledge also the students who have contributed to this work. This project is a strong example of integrating research into teaching here at Nazarbayev University. Technically, the key takeaway remains we have a two-fluid model and also the nonlinear rheology. And this combination of these two yields analytical predictions that are more realistic. This is our ongoing direction. We are in the process of developing a more unified concrete rheological model. This shows the five-parameter model, which we call the generalized yield stress fluid model. This model can be reduced to almost all the known yield stress fluid models that are reported in the literature, including, for example, the Carson model, the yield stress, the Hershey-Buckley model, or the modified Bingham model, etc. The motivation is very practical here. Rather than choosing one model per dataset, we would like to have a single consistent constitutive equation that can adopt across various concrete types. Given the generalized rheology, we then solve the forward pipe flow problem, where the inputs will be the pressure drop, the pressure gradient, so delta P over L, pipe radius, and the rheological parameters. And the output will be a flow rate pressure drop relation. And this becomes the core forward model that can later be embedded in the two-fluid pumping framework. For this very complicated five-parameter generalized yield stress fluid model, even to solve the simple pipe flow problem becomes non-trivial. However, with the method that we have recently developed, we have obtained a closed-form solution, closed-form expression that connects flow rate and pressure drop, pressure gradient. With this result, we can combine it with our two-fluid model, and then we can derive expressions for the flow rate pressure relation, where we can describe both the bulk concrete and also the yield stress fluid using this generalized yield stress fluid model. Here, we can naturally distinguish between two cases for CVC and HCC. So CVC represents conventional vibrated concrete, while the yield stress is relatively large. So in this case, for the bulk concrete, there's only the plug flow region. But for self-compacting concrete, due to the relatively low yield stress, then we can have sharing and also plug flow for the bulk concrete. So here, the bulk rheology will play a stronger role here. This slide shows the direction we are building forward, a two-fluid pumping model where fluids can follow the generalized yield stress fluid model. We're also developing computational tools like this interface shown here to explore how those rheological parameters affect the pressure flow relation. To summarize our work so far, to our understanding, reliable pumping prediction requires two key physical elements: nonlinear rheology of the concrete and also the lubrication layer formation. Based on that understanding, we have developed an analytical framework that unifies rheology and non-Newtonian pipe flow to derive predictive pressure flow relations. However, the practical challenge lies in the measurement. Even if the forward model is accurate, lubrication layer thickness and lubrication layer fluid properties are hard to measure directly, especially on-site. So now we are working towards reformulating concrete pumping as an inverse problem, given pumping data could be from real experiments or could be those predicted from our physics-based model. Can we infer the rheological parameters and also the lubrication layer characteristics? This is where machine learning comes into the story. We are currently exploring various machine learning approaches for parameter identification for the inverse problem. This is still work in progress, and I would like to acknowledge my students and the colleagues at Yanwei University and also collaborators at the China State Construction Engineering Corporation for the collaboration. And I also acknowledge the funding from Yanwei University and also the Science Committee of the Ministry of Science and Higher Education of the Republic of Kazakhstan for supporting our research. So thank you for your attention. And my contact information is shown here, and I'll be happy to take questions. So thank you.